This video is on the applications of exponential functions. Let's recall. An exponential function as a graph would give you an L-shaped curve. Example 1, we have y is equal to 3 times 1.2 to the power x. This is represented by our red curve. You'll notice that as it's increasing, it increases very fast, and as it's decreasing, it gets smaller and smaller, but it will never touch the x-axis. On the other hand, we have the blue graph, y is equal to 2 times 0.7 to the power x. The graph is getting small very quickly, and once again, it also does not touch the x-intercept. So just key features, we're going to always have an L-shaped graph. It increases or decreases constantly. So for example, our blue one, it's always decreasing, and the red one is always increasing. The last thing we should note is that a y-intercept exists, but the x-intercept does not, because it never touches the x-axis. About exponential functions, the general form is y is equal to abx. Now you'll remember from exponent rules that a is separate from the b to the power x. Because a and b are not together in a bracket, the a is a coefficient. And then b to the power of x is a power. In a national park, a wolf population is expected to increase by 7.8% per year over a 15-year period, starting in 2022. This graph is represented by y is equal to 125 bracket 1.08 to the power x, where y is the population of the wolves and x is the number of years after 2022. Now, we have a graph here. It's asking us to label the axis of the graph. This is our x-axis, and they've told us that the x-axis is the number of years after 2022. Secondly, y is representing the population of the wolves. So let's use this graph to determine what the initial population is. Initial population always happens on the y-axis when x is equal to 0. Now we notice that the y-intercept here is 125 and 0. So we can say that according to the graph, there are 125 wolves initially. According to the equation, we could do the same thing. Initial population is when year is at 0. So we're going to substitute 0 into the equation. Y is equal to 125 times 1.078 to the power of 0. Now, we know that using our exponent rule, if I have anything raised to the power of 0, this is going to be a 1. So this entire power becomes a 1, and what remains, y, is equal to 125. So we know that there were initially 125 wolves. What's the expected population in 2025? Well, 2025 is 3 years after 2020. So our x value, 2025 minus 2022, x is equal to 3. Let's substitute that into our equation. Y is equal to 125 times 1.078 to the power of 3. So we put that into our calculator. 125 times 1.078 raised to the power of 3, and we have 156.59. Now we know that it's not possible to have 0.59 of a wolf. So let's round it to 157. And as usual, this is an estimate. So we can say that this is approximately 157 wolves in 2025. Okay, in 2028 or 2038, we now have an x that's equal to 16. That means 16 years after the equation was made. But in the beginning, it says that the equation is only valid for a 15-year period. So for us, it's not super accurate for us to substitute it in. It's going to give us a number, but perhaps the scientists who made the equation know that this equation only exists for 15 years because there are many things that can happen. So since x is equal to 16 years and it is outside the period of 15 years, we can't really say that this is valid. Let's do another example of this. A car is expected to depreciate 15% per year. Depreciate is the opposite of growth, so the value of your car is going to go down. You just purchased a $20,000 used car. This graph is modeled by the equation y is equal to 20,000 times 0.85 to the power x, where y is the value of the vehicle and x is the number of years after purchase. Now let's label our axes of the graph so that we know what each one represents. The x-axis is the number of years after purchase. Our y-axis is the value of the car. Now, let's look at the equation. What part of the equation indicates the initial value? The general equation of our exponential function, y is equal to abx. We have 20,000 being the a. So our coefficient of the power, a, represents the initial value. Okay, next question. Use the question to find the value of the car 3.5 years after purchase. Compare your answer to the graph. So let's substitute in x is equal to 3.5 into the equation. Y is equal to 20,000 times 0.85 to the power of 3.5. Let's put this into our calculator. And we have a value of 11,323 and 91 cents. Now, of course, When you sell cars, the numbers are a lot fluid. So even though this is the projected price, it's not necessarily exact that you are going to be selling it at this price. Okay, now for a thinking question. This graph has no end. Now we know that because this is an exponential function, and the exponential function means that it's going to go on forever. Does that mean that a car will hold its value forever? Well, this is the difference between what's theoretical, so meaning what the graph shows, and what's realistic. It's not realistic that a car is going to last forever. So even though the graph will continue on forever to say that there is still some value, our car will probably expire after 15 or 20 years.